Let us now learn about angular speed. The word speed brings up the question, how fast is something moving? How fast is this particle moving? Actually, quite slowly. You can see that starting there to come back to the starting point, it takes quite a long time. On the other hand, this particle takes very little time. So clearly, the second particle is traveling much faster than the first particle, right? When we talk about objects that are moving in a straight line, there's only one way to talk about the speed of the particle, which is to talk about how much distance it covers in unit time. But when we talk about objects moving in circles, you have three different ways to answer this question. Of course, the standard way is the distance the particle covers in unit time, linear speed, which we will measure in SI units of meters per second. This is one way to talk about how fast the object is moving. But we can also talk about how much time does it take to complete a revolution. When the object is moving in a straight line, you can't do that because the object doesn't come back to the starting point. Whereas here, it starts here and it comes back here. So we can talk about the time period, the time taken to complete a revolution. This is measured in, obviously, time units, seconds, right? So time period is the time it takes for the particle to come back to the same point. How does that measure? How fast is the particle moving? If the time period is less, then the particle is moving faster. And if the time period is more, if it takes a long time to come back, then the particle is moving slowly, right? So we can use the time period to measure how fast the particle is moving. But there is another way, a third way in which we can talk about this. We can ask the question, how many revolutions does it do in 1 second? In unit time, how many revolutions does the particle make? If the particle makes many revolutions in a single second, that means obviously it's moving faster. But if it is making very few revolutions in 1 second, that means it is moving slowly. So here we use the idea of angular speed. So angular speed talks about how many revolutions you complete in 1 second. And so the unit will be revolutions per second. Now, there are three different ways I said. Are these three different ways always the same? Let us look at this example. Here I have these two particles that are going around in two different circular paths, concentric circles. Are all the three things the same for these two particles? Let us first look at time period. You can see that the particles started together here and they come back to the same place together. That means they have the same time period. Do they have the same linear speed? What do you think? Both these particles have the same linear speed? No. This fellow travels lesser distance. 2 pi r is smaller for the smaller circle. 2 pi r is larger for the larger circle. So in the same time, the outer circle, particle moving in the outer circle, is traveling more distance. So you can just see, directly when you see itself, you can see that the particle moving in the outer circle is moving with a larger linear speed. So they don't have the same linear speed. What about angular speed? What about angular speed? Do they have the same angular speed? Think about it. Revolutions completed in 1 second. They have the same time period. That means in the same time they will complete one revolution. So that means in 1 second both will complete the same number of revolutions. So both will have the same angular speed, but they will have different linear speeds. So angular speed and linear speeds, clearly they are very different. And in this particular case, they both have the same time period and they both have the same angular speed. Looks like these two are much more closely connected. Actually, all three are connected, but these two are going to be much closely connected, much more closely connected than linear speed. So what we are going to do is to first understand time period and angular speed, their relationship. Okay, we are going to learn how to calculate these, and then we will look at linear speed. In this question, we have 4 particles moving in 4 different circles, P, Q, R and S. And we want to find out which 2 particles have the same angular speed. It is given that 2 of them have the same angular speed. Which 2? That is the question. Is it P and S, P and Q, Q and S, Q and R? Okay, what is angular speed? The number of revolutions per second. Okay, so in unit time, how many revolutions does the particle make? That is angular speed. Let us look at P and Q. Now, let's start from here. P is now going to make 1 revolution, and you can see that Q hasn't completed a revolution. Okay, or if I try to start here, when Q starts, and you see that P has already finished, Q is not yet there. So that means P makes more revolutions per second than Q. P has higher angular speed than Q, not equal, higher angular speed. Okay, so P and Q, that is definitely not correct. What about P and S? Let us look at that. P starts here, and you see that S is already finished. By the time P makes 1 revolution, S is already completed. So P and S, S is faster. S has a higher angular speed compared to P. So P and S clearly is not correct. What about Q and S? Q and S. Well, Q was slower than P. S is faster than P. So obviously S is faster than Q. You can see that if you say S starts here, by the time it finishes, Q is not even completed half a revolution, right? So S is much faster than Q. So clearly Q and S is also not correct. So Q and R, let's check out Q and R between these 2. So I'm going to look at when R is here, where is Q? Q is also at the starting point. When R completes a revolution, Q also just completes a revolution. So both take the same time to complete a revolution. So in the same time, they make 1 revolution, which means in 1 second, they will make the same number of revolutions. So both of them have the same time period and they have the same angular speed. So the correct answer is Q and R have the same angular speed, not P and S, not P and Q, not Q and S. Q and R have the same time period and the same angular speed. Think about it. In the same time, R completes a revolution, Q also completes a revolution. But Q travels a smaller distance, R travels a larger distance. So R has a higher linear speed compared to Q, but angular speed both are the same. So here the question was about angular speed. Q and R both have the same angular speed. We know that time period and angular speed, they are very closely related. But exactly how are they related? That's what we are going to see now. Time period, T, we usually use capital T for this, is the time it takes to complete 1 revolution. So let us look at this particle. This particle goes around and comes back in 1 second. It starts from here and completes it in 1 second. So the time period is 1 second. This particle takes a long time. It takes 5 seconds to complete a revolution. So its time period is 5 seconds. This particle is really fast. It finishes 1 revolution in half a second, 0.5 seconds. So you can see that they all have different time periods. But what about angular speed? Angular speed, omega, this is the Greek letter omega. This is the number of revolutions per second. The number of revolutions per second. Well, this makes 1 revolution in 1 second. So how many revolutions will it make in 1 second? 1 revolution. So 1 revolution per second. So we write it as 1 RPS. RPS stands for revolutions per second. So what is the angular speed of this particle? 1 RPS, 1 revolution per second. What about this particle? This particle takes only half a second to complete a revolution. So in 1 second, how many revolutions will it make? It will make 1 and 2, right? It will make 1, 2. In 1 second, it will make 2 revolutions. So 2 revolutions in 1 second, 2 revolutions per second, 2 RPS. So the angular speed of this particle is 2 RPS. What about this fellow? This takes 5 seconds to make one revolution. So in 1 second, what do you think it will do? 1 second, it is not even completed a revolution. So it takes 5 seconds to make one revolution. So in 1 second, it would have only gone 1/5 of a revolution. So 1/5 of a revolution in 1 second, 1/5 revolutions per second. 1/5 is 0.2, 0.2 revolutions per second, 0.2 RPS. So from this you can see very clearly that omega, the angular speed in revolutions per second, and the time period in seconds, very simple relationship. 5 seconds, omega is 1/5 revolutions per second. 0.5 seconds, omega is 1/0.5, which is 2 revolutions per second. So very clearly we can say omega in revolutions per second, RPS, is 1/t, where t is in seconds. Now this is very important. Don't remember it as omega is equal to 1/t. You must remember it with units, because we're going to use many different units to talk about angular speed. So when we are talking about angular speed in revolutions per second, then it is equal to 1/t, where t is the time period but taken in seconds. What if I took the time period in minutes? Then you will be talking about revolutions per minute. So we can also write omega in RPM. RPM stands for revolutions per minute. So omega in RPM is 1/t, where t is taken in minutes. So the same idea, omega is 1/t. We can use it for revolutions per second if t is in seconds, and revolutions per minute if t is in minutes. Okay, but do I have to only talk about revolutions? Can't I talk in terms of degrees? Of course you can. You know that one revolution is 360 degrees. So in 1 second, instead of saying it makes one revolution, I can say it makes 360 degrees per second. So omega can also be written as 360 degrees per second. Just a different unit, different value, but one revolution per second is the same as 360 degrees per second, because one revolution is 360 degrees. So 360 degrees per second. What about this fellow? Well, this is 2 revolutions per second. So 2 revolutions per second means one round will be 360 degrees. The second round will be 360 plus 360. So totally 720. So you can say omega is 2 revolutions per second. 2 times 360, 720 degrees per second. And what about this one? Well, it is only traveling 1/5 of a revolution. 1/5 of 360 is 72 degrees. In 1 second, it only travels 72 degrees. So omega is 72 degrees per second. 0.2 into 360 is 72 degrees per second. So of course, we can talk about omega in degrees per second. But then you can't say 1/t. Then you will say 360 degrees divided by the time in seconds will give me the omega in degrees per second. So you can say omega in degrees per second is 360/t, where t is taken in seconds. So 360 degrees divided by the time period. Because the time period is telling you that you have traveled 360 degrees. So 360 degrees by the time that it takes, which is one time period, will give me the angular speed, but in degrees per second. So you see, you can say omega is 1/t if you want to use revolution per second, but if you want to talk about degrees per seconds, then you must talk about 360/t. The most important or the most common form of omega is using a new unit of angle called radians. So the best unit which you will later learn is omega in radians per second, and there it turns out to be 2π/t. It may look very messy, 2π/t. Obviously 1/t looks much better, but it will turn out that this will be very useful in many other different circumstances. So we will study this later. So you may come across omega defined as 2π/t. This is the most commonly used, and I would also say that is the best possible way in which we can define omega and use omega. But in degrees per second, we will write 360/t. In revolutions per second, we will write 1/t. So these are also things that we will use quite commonly.